Hello. In our previous lecture, we looked at some of the performance metrics of a typical optical sensor. So these are basically the quantification of the performance of an optical sensor, and we looked at several parameters like measurement range, minimum detection limit, sensitivity, response time, accuracy, and precision. And specifically, when we were talking about minimum detection limit, we were saying that this minimum detection limit is limited by the noise in the optical sensor. So, one of the questions is, can we possibly reduce this value of noise? So we can if we can bring down this value of noise, then you could possibly bring down the value of this minimum detectable limit also, so you can move closer to zero. Okay, so that brings up a interesting question. How do we deal with noise? How do you mitigate noise? Okay, so that's what we're going to be talking about. So let's ask ourselves the question, how to improve minimum detection limit. Okay, so what we are typically talking about is we're trying to see how we can reduce noise. So let's look at this graph here as a function of time. We are observing some current or maybe some voltage representing the measurement, right? So when we look at this, the measured value may be the measurand basically maybe is holding at this value, right? But what we actually measure in our sensor is it's actually something around that value, but not exactly that value. So we have essentially noise that adds on to the signal that we are trying to measure. So your actual measurement might look something like this, maybe even some stray points like this, right? And so on, right? So you have a bunch of points around the actual value that you are trying to measure. So much so that if you take a histogram of all these points, that histogram is going to look something like this. Okay, and it's typically a Gaussian random variable, right? So this is actually a Gaussian random variable, because the noise sources that we were looking at typically all this short noise process, the thermal noise process, the APD multiplication noise, and so on, they're all characterized by Gaussian random process. So we know that this would correspond to some mean. So we can call that say Vs is corresponding to the mean of all these samples, and it's also characterized by certain variance, which is what we were looking at previously as sigma square. Okay, so this variance and specifically the root of that, which is the RMS value, the standard deviation, that standard deviation is going to be determining the minimum detectable limit, right? So if you want to improve that minimum detection limit, you need to make this thinner, right? You need to basically reduce that sigma square as much as possible, and so that's essentially the problem that we are going to look at. So one way of potentially doing that is to do multiple sets of measurements. So you could do one set of measurement like this, and so this is actually the number of measurement. So you could essentially do one more measurement. Let's say the value of the measurand is actually staying the same. Then you could do one more measurement. Of course, what we are going to see is when you do these measurements at different times, they are not necessarily going to replicate. The noise is not going to replicate. Okay. So essentially, we are looking at this as another Gaussian random variable, okay, which will once again show the same mean. So if we call this Vs1, let's call this Vs2. It's typically the same mean, and if we call this sigma 1 square, you get get sigma 2 square over there. And since the noise characteristic is once again it's this broadband white noise, additive white Gaussian noise is what we are looking at. So the noise characteristics don't change over multiple measurements, right? And because of that, if you look at the overall signal to noise ratio, okay, we can basically add multiple measurements. Let's say we are adding these two measurements here, and then if you look at the signal to noise ratio, and let's say with respect to the RMS value of the signal, then that will correspond to basically you can add two Gaussian random variables, right? That's what we are doing, and what we get in this case is Vs1 plus Vs2, the means add, and when it comes to the variance part, the variances add sigma 1 square plus sigma 2 square, but since we are defining everything with respect to the RMS value, you have to take a root of that. And when we actually look at this, it's the same sensor and the same measurement you are doing, so your Vs1 and Vs2 are likely to be the same. So if you say Vs1 equal to Vs2 equal to Vs, then you can replace the numerator by 2 times Vs, and similarly the noise is going to be having the same characteristics or the same variance. So sigma 1 equal to sigma 2 equal to sigma, if you say, then this is going to be root of 2 times sigma square, okay. So that is essentially root 2 times sigma in the denominator and 2 times Vs in the numerator. So what you essentially get is root 2 times Vs over sigma, right? And Vs over sigma, what does that denote? That's actually the signal to noise ratio, okay, for when we just consider one set of measurements, when n equal to 1, okay. So in general, what we see is your SNR, RMS SNR of if you can extend this basically to n number of measurements. So, if you say the SNR that you get after n measurements, if you are basically adding all these corresponding samples and then when you look at it, you essentially get you can extend this and you can prove that this is corresponding to root times n compared to SNR of n equal to 1. Okay. So, that is actually a fairly powerful way of improving the signal to noise ratio of your optical sensor. Okay. So, you basically do n measurements and then through that you improve your signal to noise ratio. And this is actually a very powerful concept that is used in what we saw previously at the beginning. We were just going through an overview of the course, and at that time we were talking about distributed fiber sensors. And in distributed fiber sensors, the amount of backscattered light is typically very low, so it's actually corrupted by noise at the optical receiver, and because of that the signal to noise ratio is typically quite poor. And to improve the signal to noise ratio, we are actually making use of the point that you could you send one pulse, you get backscattered trace, you wait until you collect all the samples from the farthest end of the of your sensing fiber, and then you launch another pulse and then you get the backscatter trace. So, essentially like this you have multiple measurements that are done, and then you basically take the first sample of each of these traces, add them together, take the second sample, add them together, and so on, right? And since these are all certain the variation is because of some Gaussian random process, when you add, basically you get essentially this sort of an improvement in the signal to noise ratio. The signal to noise ratio improvement with respect to one measurement is root of n. So, if you do for example 1000 or 100, let's say it's an easier number. So, if you do 100 such measurements, then you get improvement in signal to noise ratio by a factor of 10. So, it's quite useful there. But mind you, one thing you are assuming is that the response of your whatever perturbation you're trying to measure, that perturbation response is consistent over a period of time, over the period of time that you're taking to do all these measurements. It is not changing. Of course, what we have shown here is that it's holding at this value, right? The let's say this is a gas concentration. So, the gas concentration is holding at a steady value. If you are holding at that steady value, then you can afford to do such averaging. So, this is what we are calling as, through averaging you are essentially getting this improvement in the signal to noise ratio. So, one thought is, can we actually do we have to do multiple sets of measurements? Okay. Can we possibly do this averaging across this time scale itself? Okay. So, as long as each of these points are independent from each other, right? Because it's only when they are independent you can actually do this this sort of simplification here. So, that's when you get this improvement in the signal to noise ratio. So, as long as each of those points are independent from each other, you could possibly do an average across n samples. So let's actually look at this in a separate page. So what we are talking about is your signal is holding at this level. Now, as we talked about, the noise samples may be something like this. So it's varying with respect to time, and then what you could possibly do is to take a block of samples. So you say, okay, I'm going to take a block of so many samples, okay, and across this block I will do an addition. Okay, if I do that, then if the mean value remains the same, so then it's the same expression that we saw over here. The mean value remains the same, but this each of these could potentially have this characterized by a certain random process. So you could essentially get an improvement in this in the signal to noise ratio because of this. So you would basically do let's say a mean of this, okay, and you would represent that by one point here, and then you go to the next set of samples, do a mean of that, and you get a representation like this, and so on. So you can keep doing this, and eventually what you will get is something that that may look like this, okay, that is closer to the value that you are trying to get, and this is what you call as run length averaging. Okay, so the question is, can we, when can we do this run length averaging? And real question is, how do we decide on the value of n? Okay, so how do we decide on the value of n, where n is actually, we're talking about the block of n samples that you are trying to average. Okay, how do we decide on n? Well, in general, the principle that you want to keep is that your processed data, okay, should preserve the highest frequency component in the measured signal. Okay, it should preserve the highest frequency component in the measured signal. So far, we've been looking at the value of the measurand being equal. I mean, or being constant over time, right? Because this is measured over time. Okay. What if it is not constant? So let's say this is actually as a function of time. We are looking at this voltage, and just like before, we have a certain level, but after a certain time it actually jumps to another level, whatever quantity that we are measuring. Let's say the example that we took last lecture was gas concentration. Let's say the gas concentration is suddenly jumping after a certain time. Now, in this case, when we look at the measured values, the measured values are going to be something like this, let's say, and maybe a measured value like here, and then it's going to have some values at this other level. Okay. So now what you do? So if you employ this run length averaging, right, in this sort of a case, and if you go with say n equal to 10, so you are basically taking 10 samples, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you are representing with one value, right, and then you take the next 10 samples and you represent with another value, and so on, right. If you do that, then what you are likely to get is something like this, right. So you will have values closer to this the ideal value that you are trying to measure. But as you approach this, as you start averaging across this, the average value is going to now change. So it will basically go like this, and then after a certain time it will be like this. So essentially what happens is, then you are doing this, you are you end up smoothing this transition. So this is for n equal to 10. So you say, okay, n equal to 10 actually may not be a very good value because it doesn't actually represent this transition very well. Okay. So what do you do? Well, maybe I don't want to go to n equal to 10, maybe I can do n equal to 3 or 4, let's say n equal to 4. So if you do n equal to 4, then you might get some value like this, like this, like this. So since you are adding only lesser number of values, okay, your signal to noise ratio improvement is not going to be as much as it's in the case of n equal to 10. But what you gain in this process is that the transition is relatively well preserved. So you might have a signal like that. Okay, this is what you get for n equal to 4. But in this case, the transition is relatively better sort of preserved. Okay, so this is one of the key points to understand. Essentially, what we are doing when we are doing run length averaging is you are doing what is called low pass filtering. So you are essentially losing some of the high frequency spectral components in your signal. Okay, so that's something you have to be wary of, and if you want to actually extend the cutoff frequency of your low pass filter so that you can bring in some of the high frequency components, you also start actually bringing in noise, and because of that the improvement in the signal to noise ratio may not be as high. Okay, so that's something that you have to be very conscious about. Okay, so overall, so if we go back and look at this question, how do you decide on n? It's a trade-off typically. So, large n, high SNR, okay, you have better SNR, but low, so what do you call, low bandwidth, if you may call that, because you are essentially smoothing over this transition, right. So, low bandwidth, whereas if you do small n, you get only moderate improvement in SNR, but moderate, so you get moderate bandwidth also. But anytime you are doing this run length averaging, you are compromising on the bandwidth of your signal, right. So, your signal, if you see the red things, the signal is actually responding quite quickly, but because of the run length averaging, you are starting to actually have this roll off around the transition. So, you are compromising the bandwidth in this case, okay. So, that is important to understand. So, so what do we learn from this overall? So, averaging overall may not be suitable for applications where you need a real time processing of fast varying signals, okay. So, it may not be suitable for real time processing of fast varying signals, but nevertheless it could be quite useful in in distributed sensing of for example civil structures, okay. In distributed sensors in civil structures, if we are trying to pick up strain or temperature, those things change over much longer time scales, something the order of seconds or even minutes. So, you have that much more time to capture your signal and improve your signal to noise ratio. So, in those cases, this is actually a very, very useful tool. It is quite useful in distributed sensing, where the whatever you are measuring is not changing much quickly with respect to time, okay. So, that is actually an important thing to remember, realize basically. So, saying that averaging, when you use averaging is when you can afford to actually make multiple measurements and improve your signal to noise ratio through that. So, that is about averaging. So, now let us go on to looking at another tool that may be available to you as far as improving your signal to noise ratio is concerned. And that tool is spectral filtering, okay. When you look at the signals that you want to typically pick up using a sensor, in a lot of cases you have the signal bandwidth. So, if you are looking at this, the spectrum of the signal, so this is amplitude as a function of frequency, right. If you look at the spectrum of the signal, that signal spectrum may be something like this. It's only available, it's confined to a certain range of frequencies. Whereas if you think about noise that you have, that noise is actually spread across, it's like we talked about, it's typically white noise, so it's spread across all these frequencies. So this is noise and this is your signal. Okay. If that is the case, then why do we need to have receiver with very high bandwidth? I mean, your photodiodes normally are having a bandwidth in the order of hundreds of megahertz easily, and so your receiver, your transimpedance amplifier could also support tens of megahertz of bandwidth. Why you need to have such a large bandwidth when your signal is, let's say you are picking up some environmentally changing parameter like strain or temperature, humidity and so on. Those signals are actually not changing very fast. They are typically having all the components within a kilohertz of bandwidth. Okay, so the question is, if this is the case, then what you could possibly do is you could do low pass filtering. Okay, so if you do low pass filtering, essentially we are saying that we apply a filter that cuts things off at a certain frequency. Let's say FC is the cutoff of your low pass filter. Now, of course, FC is typically like a corner frequency, and then there is actually a very gentle roll off of the filter response. So there are issues related to this, how sharp a roll off you need. If you need a higher, if you need a sharper roll off, you need to go to a higher order filter and so on. So there are other issues. I'm not going to go into details of those, but the key point here is this may be enough to sort of preserve your signal, which is only within this region. Okay, and the advantage here is that your noise now is also limited only over this region. So you are essentially improving your signal to noise ratio. Okay, so that's a reasonably easy concept to understand. So you could do spectral filtering if you know that your the signals that you're trying to capture have only information content over a well-defined band of frequencies. Okay, so you, in that case, you could just take out, send it through a filter that allows only those frequencies. So in which case you are also reducing the noise, and thereby you are improving your signal to noise ratio. Okay, so let's look at an example of one such filter. So I'll take the example of filter that we use widely in our laboratory, which is called Savitzky-Golay filter. And if I once I tell you how we do this, then you will understand why we are picking up this particular filter. Okay, of course there are lots of other filters, Bessel, Chebyshev, you name it, Butterworth. There are so many other filters that are already existing. So you could look at any one of those. things, but I'm just taking one example of that. So let's say the signal once again that you want to measure is something like this. It's let's take the easy case first, where the quantity that you are measuring is not changing with respect to time. So this is once again the voltage as a function of time. So what does a Savitzky-Golay filter do? Well, as before, we have all these samples, right? So there are these noisy type of samples. Something like this. What you define in a Savitzky-Golay filter, it's in some ways similar to run length averaging, in the sense that you are defining a block. So you would basically say, okay, I'm taking a block of 5 samples. Okay, what you have to define for the filter is you have an order of the filter, and you have window size. Okay, so in this case we are doing over 5 samples. So let's say that corresponds to a window size of 5, and I'm going to do order 1. Okay, if I do order 1, that's actually a first order polynomial. Okay, so that's just a simple straight line fit. Okay, so what it's going to do is try to take these 5 samples and do a fit, a straight line fit. Okay, so if we do that, it might get something like this. Okay, and once we have that, then basically what it does is it replaces this sample with the fit value. Okay, similarly, just the same way we did in run length averaging, it goes on to the next sample. So it takes the next 5 samples over here, and then it does one more fit across this. So this fit might look something like this, and then correspondingly the point that you get is replaced by this. So it keeps replacing all the samples with this fit value, and what function we fit is determined by this order, whether it's first order just a simple line, or if you go to 2, it's a quadratic function, go to 3, it's a cubic function, and so on, right? So you can actually define different orders. But if you do this, essentially if you keep doing this, you will find that your signals are now hugging closer to your actual value that you want to measure, right? So so you get an improvement in the signal to noise ratio, and that improvement is going to be more, just like we saw in run length averaging, if you increase your window size. So then once again the question is, what should be your window size? Do you always pick up order 1 and so on? And the answer to that is, well, depends on what is the expectation in terms of your frequency content in your signal. Now if you say your signal voltage as a function of time has got some high frequency components, let's say in this case, once again we are talking about having this transition over here. If you have such a transition in your signal, then you apply the same thing. So first of all, let's represent all these noisy data points. Then if you do this order 1 window phi over here, it works very well in this region, but when it comes to this region, it will tend to smooth over. Okay, so you might actually get, I'm just going to draw the effect of that. So if you do a order 1 window phi type of things, it might actually look like this, but it might smoothen over here and then it might look like this. Okay, so this is for order 1 window phi. Okay, in such a scenario, so you are losing some information over here, so you want to preserve that information. So what is the better filter to go for? Maybe you can go for a second order filter. Okay, so if it is a second order filter, then it takes all these samples and does a parabol, it's a quadratic fit to this, and then replaces the sample and so on. And when it comes to this transition, you can still do a quadratic fit over this, as long as it's just going one way, it should be fine. Or if you really want to preserve this thing, you can go to a cubic fit. That may be even better in the sense that it preserves this. But what is the downside of this? If you do, for example, the quadratic fit might actually start looking like this. So what you see here is the transition is better, okay, because we went to order 2 and we're still keeping a window size of 5, right. The transition is preserved better, but in this case, if you look at the signal to noise ratio, right, it's still actually not much better compared to what you started with. Okay, so that's those are the kind of trade-offs that you have to deal with while you are deploying some of these filters. Yes. Okay. So maybe I can just summarize what I said here. Basically, low order, large window, you have best SNR improvement, right, but poor basically bandwidth, right, whereas high order you say low window size, then only a moderate improvement in SNR, but better bandwidth. Okay, but the whole point is, this is actually the Savitzky-Golay filter is actually a flexible way of tuning the spectral characteristics that are required. Okay, so a flexible way of tuning the spectral characteristics required to process your signal. So that's actually a powerful way of doing an improvement in the signal to noise ratio.